Okay. Well, good morning. Happy Monday. Can see we have a little bit fewer people than last Thursday, and probably reaching out to you to see what's going on. And right now, we're currently fine with our progress. So just want to have a quick questions, basically. I heard that we're gonna have a holiday this Thursday. So is that the spring recess? Anyone can help me out on that?
It is.
Yeah,
Yeah,
spring
it's spring
recess.
recess.
So we won't have class on Thursday,
Correct.
and then we'll probably have to delay our homework, as indicated by Tom last time. So I put in a new homework deadline for the number 6 on Shear, and it's supposed to be due next Monday now. And most of the content in homework number 6, we're going to cover them on Monday and on Wednesday as well. So we should be able to do them before the spring recess. Um, and in terms of the some of the makeup exam, folks, you know who you are. We're going to take the makeup, and that's going to happen on Tuesday, 6:30 to 8:30 p.m. Let me say it again. So Tuesday, which is tomorrow, 6:30 to 8:30 p.m. I will send an email tonight, this later afternoon, matter of fact, and I will send a reminder tomorrow morning as well. So
Professor,
let
I
me
have a
say
class at that time.
Oh, you have? Louisa, if you have, you just have to reach out to me and we have to set up different time for you. So the previously, wait, Louis, you say 6:30 to 8:30 p.m. you have class at time?
On Tuesday, yes.
Oh, okay. So send me email. Let me reschedule time for you. We have a different set exam for you, maybe. Okay?
All right.
Yeah.
Thank you, sir.
Yeah,
I'll do that then.
not a problem. Yeah. So I will send the email out about that, and it's gonna be 2 hours. So if you have conflict, just Louis, as Louis did, just email me so we can set a different time. All right. Okay. So before I
I'm
get
sorry, I
started,
just got in the call. The what is this about?
oh, this is about a makeup exam. I don't think you're
Okay.
in that group. I send out email and we discussed about it. If you're not in the group, you don't have to attend. Okay, this is a separate event. All right. I just want to mention because few of us did not answer my email. So quickly, I just want to mention here. Okay. All right. So before I continue with shared design, any question for me regarding the course or anything else? Folks, anything? Okay. All right. So let's continue with share then. Okay. So first of all, let me resume sharing. Let me do this share screen. Okay. All right. So last week we talked about shear design. All right. And I have to emphasize on this is that we talked about the shear design using the code ACI 31814, that is, not the ACI 31819. And you may ask why is that 31814 is a base for 31819. So I want to cover 31814 first and show you the differences and you know how to work with both codes. And in reality is that a lot of current design and repair right now are ACI 31814 and the textbook is on ACI 31814. So I want to teach both so you have more information. And if you're interested, know that the newest version, which is the reinforced concrete design and mechanics by James, right? And that is on the ACI 31819. That version is version 9, and that will be out later this spring. So if you are interested, you can also search for that. Okay. All right. So that is the information about design code 318 and 14. So I want to give you an example of how to design it, right? So first of all, let's just write down here. So example of shear design, okay? Example of shear design. And this is, let me just emphasize so you guys won't confuse. This is 31814 version, okay? This is 14 version. All right. So first of all, let's take a look at the section, right? For shear design, it starts with a section as well. So example, I have a rectangular section just like so. And this rectangular section have top, sorry, bottom reinforcement tension, right? So I have 4 number 8 bars. All right, this is for number 8 bars. Okay, and the dimension of the section has a width of 12 inch and has a height of 24 inches. Okay, and to make things easier, we also showed you that it has a depth of, and that is ds equal to a 21.5 inch. So you pretty much can figure that the concrete cover here is about 2.5 inches. 2.5 inches. Okay. All right. So this is the section, right? And additional information is that if you look at the section, right? So we're talking about simply supported beam for this case. Okay. For this case, simply supported beam for this case. All right. And it's under uniform distributed load. So the critical shear diagram looks like this, a triangle for simply supported beam, of course. And then the shear or the section we are looking at right now, say if I call this section AA, okay, is right here. All right. So this is where the section is right here. Okay. And you notice that the section is not exactly on the support. Okay. So where exactly the section is at, I just want to see a zoom in picture. So if I zoom in here, okay, zoom in here, all the details will be exposed. And you will see that it's a support, which is a column. And by the way, this is here, okay? Support, which is a column. And I have a beam, this is a side view, of course, sticking out like that. And I have a neoprene pad. And this neoprene pad is essentially a layer of rubber with steel thin sheets, plies, right? And then this is sitting right on top of it. And this is the center line where the center of the column and supports that. And when we talk about the spacing, when we talk about the critical spacing, sorry, I have more people joining here. It's not exactly on the support, right? Where exactly is that? It's actually spacing D away. Sorry, let me just clarify this. D away from support. So that is, if I draw my column here and use my red, this is edge of the support. So it's essentially distance D, and D is the depth, okay? You can say ds as well, ds away of this section right here, okay? And the diagonal crack looks just like that, 45 degree. Oops. All right, so this is the section AA we are talking about, okay? And mind you that this is 45 degrees. This is 45 degrees roughly. All right, so if we were to design shear, we're gonna take the shear force right here at section AA as the design shear force, Okay, so it's a little bit different, And we will talk about this right after we finish example, okay, where this typical, and this is so-called critical section, where this typical critical section is at, okay? All right, okay, so just a quick reminder that there's a little bit details on the design side of it. We'll talk about this after the example, okay? So I just want to quickly give an example. So for the given section, this is the question. So given section on the left, and we want you to check if the section is adequate to resist shear force at, of course, section AA, and we call it VU, which is applied or factor shear, okay? And so if not, okay, design web reinforcement. What does it mean? It means that we want you to see if the concrete contribution itself can handle the shear. Now, if not, we have to provide a reinforcement. And what is the area reinforcement need to be applied? And what is the spacing between the stirrups? Those are something we need you guys to design for, okay? And now here's our basic, the concrete properties for KSI. Steel strength for the stirrups, 60 KSI. Whenever you see a T, this is indicating that is for stirrups. All right. And now this is for normal weight concrete. Very important, okay? Normal weight concrete, so meaning lambda equal to 1. And this is simply supported beam. Now this, the boundary condition simply supported. You probably don't need to know, but that's the conditions we have. So we have a set of shear force for you to check. So Vu can equal to A, 12 kips, B, 24 kips, C, 54 kips. Just keep increasing. D, where we at? 77 kips. And E, 128 kips. Okay, so here's a problem. Okay, here's our problem. All right, to solve this, right, let's take a look at the A first. A, 12 kips. Okay, so first thing first, I have applied shear 12 kips. I want to see if my nominal shear resistance is sufficient, so I have to make sure VBN is bigger than or equal to VU, right? That is applied shear. And I know from the concrete contribution VC, that equal to 2 lambda square root of F prime C, BW, and D. Okay. Now you notice that whenever I use shear design equation, I don't differentiate as ds or dt because d in this shear design always equal to ds. Okay, always equal to ds. All right. So that is the contribution from concrete. So let me bring the numbers. 2 multiply lambda equal to 1.0 since normal weight concrete multiply 4,000 psi. Okay, psi, and then multiply 12-inch, which is the width, okay, and then 21.5-inch, which is the depth. All right, so that gives me a VC of 32.6 kips. And that is how much concrete can contribute to the resistance shear. Okay, so with that, let me do this. VVC equal to 0.75, 0.75 multiplied by 32.6 kips. Okay, and then that is 24.5 kips. All right, and this value, you can see that's already larger than the 12 kips applied shear. Okay, so seems like my section is adequate, but on top of that, I need to double check one thing, and this is from the code. How about half of VVC? Okay, so this is important from ACI 3.18.14. Okay, I have to check how about half of VVC. Okay, so this turns out equal to a 24.5 kips divided by 2, and that gives me a 12.25 kips, which is still bigger than the applied shear 12 kips. Okay, so in this case, right, in this case, ACI says if half of VVC, that means the factored contribution from the concrete section divided by 2 is larger than VU, meaning you have more than enough resistance from the concrete section already. Okay, in this case, only minimum web reinforcement is needed. Means you just need to provide a little bit of reinforcement, and that's fine. Okay, that is fine. So in other words, you just have to provide a Vin mean, right? AV minimum. Okay, so that is
Professor.
what it says here. Yes,
What did you say about D equaling DS?
you mean here?
Yes.
This is just for shear. Whenever you see a D, that is DS. So in essence here, this is D.
Okay, that's just because we're doing shear. Okay, makes
Yes,
sense.
yeah.
Thank
For
you.
flexure, yeah, for flexure you have two Ds, right? You have DS and DT, they're different and they have different purpose, right?
Okay.
You use DT for finding the strain, finding the phi, and you use DS to find the moment capacity, right? So slight differentiation. Okay. All right. So this is the requirement. It says, okay, if I satisfy the requirement by only half of the concrete contribution, I just need to provide a minimum reinforcement. That's it. Okay, so that's very easy. Now the second part, B, problem B, I bump up my shear to 24 kips. Okay, so naturally you find out that phi VC, which calculated here, equal to 24.5 kips, and that is slightly bigger than the applied shear, which is 24 kips. Okay, now for this case, I definitely know that half of phi VC is not greater than VU, so I cannot provide just the minimum reinforcement AV min now anymore. Okay, but still, you see, this is concrete contribution and this is applied shear, meaning I don't need any calculations on the shear reinforcement. Okay, so in the sense is that here, let me just put a mark here, asterisk. So no need to compute VS, which is the shear contribution from the web reinforcement. Okay, but we still have to use S max instead. We still have to use the spacing control to insert minimum amount of reinforcement. Okay, how? I'm going to show you. So S max, in this case, that concrete is already taking care of most of the shear, but we need to satisfy these requirements. Okay, now what are these requirements? That says D over 2 divided D over 2, that is 21.5 inch divided by 2 equal to 10.75 inch. Okay, and 24 inch spacing, and then AVFYT divided by 0.75 square root F prime C and BW. Just one of the equation, right? Bring a number, this is 0.22 inch squared, okay? 0.2 inches squared multiplied by 60,000 PSI divided by 0.75 multiplied by square root of 4,000 PSI and multiplied by 12 inches. Okay, you may say, whoa, wait a minute, Bob, where does 0.22 inch square coming from, right? This is coming from the fact that we are assuming a number 3 stirrups. Okay, you say, you sneaky Bob, yeah, you just slipped this number in, didn't you? Yes. So we always assume number 3 or number 4 stirrup. Okay, now for number 3, each leg is 0.11 inch squared. That is area, right? So AV in this case equal to 2, number 1, number 2, right? So 1, 2, 2 multiplied 0.11 inches squared, and that gives you the 0.22 inches squared. Okay. All right, so that is where it's coming from. And I got this number to be finally arrived at 23.2 inches. Okay, now don't forget the last equation, AVFYT, have to divide by 50 BW. Okay, and this equal to 0.22 inch squared, we just calculate that, multiplied by 60,000 PSI, and that is yield strength for the stirrups, and divided by 50, and multiplied by 12 inches. And I got this number to be 22 inches. Okay, now I have 4 numbers, right? 10.75, 24, 23.2, 22, and I'm trying to find the least of it. So naturally, this governs. 10.75 governs. Okay, now with this, I would say, okay, in this case, I am going to provide a spacing of S smaller than S max, okay, which is 10.75 inch. So why don't we use 10 inches as a spacing? And this is assuming a number 3 stirrups. Okay, so now that is the design for B, 24 kips. Okay, I just want to observe the difference. What is the difference between B and A? Okay, so naturally lower shear force in A, so we end up seeing that half of the concrete contribution is sufficient to resist that. So I don't even have to provide the spacing. I just need to put a minimum amount of shear reinforcement, and that's enough. Okay, now for B, which is higher shear force, I no longer have the case where half of the concrete contribution will suffice. Instead, I need the entire section of concrete to resist that shear. So in this case, I have to invoke my spacing requirement from the ACI to get my spacing. And when I provide the spacing requirement, I already assume the size of the stirrups I was going to use and then come up with a correct number at the end of it and provide this spacing to resist the shear. Now I'm going to do a division line here because both cases here, A and B, both cases here, I have no web reinforcement designed or contributed. Okay, I have no web reinforcement contributed. You say, wait a minute, Bob, you're conflicting. Why? Because you provide the spacing and you said I'm going to use number 3 stirrups. And now you're saying you don't have any contribution from the web reinforcement. So what's going on? Now the answer to that question is, look, we provide a minimum shear reinforcement. They don't have to participate in resisting shear. They're just there for safety measures in case, right? For accidents. When the concrete is lower strength concrete, there's a pocket hole, they're just under strength of the member, so on and so forth. So we don't have to actually calculate how much shear has to go into the reinforcement. So that is A and B. All right, so that is kind of critical. You have to understand that. Okay, now moving forward, I'm going to case C. All right, in case C, I bump on my shear significantly to a number of 54 kips. So immediately, I'm going to use red color here. Immediately, phi VC only equal to 24.5 kips. This is much smaller. This is much smaller than the 54 kips applied shear. All right, so definitely stirrups needed. Okay, or using the proper terminology, web reinforcement needed. Okay, web reinforcement needed. All right, so in this case, we're going to calculate how much contribution that the stirrup have to give. So phi Vn now has two parts. That is the concrete contribution Bc and shear contribution Bs from stirrups that has to be bigger than Vu. All right, so what I'm going to do is I already know the contribution from the concrete maximized at 24.5 kips. All I have to do is compute what is the required shear resistance from the steel, and that is Vu divided by phi minus Vc, and that is 54 kip divided by phi. And what is phi for shear? Always 0.75. You see? So all these details, okay? For shear, always 0.575, okay? Have to switch your mindset from flexure to shear, okay? So that is phi, and then minus a VC. What is VC? 32.6 kip. So wait a minute, isn't it 24.5? This is 24.5 divided by phi, okay? 32.6 kip. And this is 39.3 kips, and that is, of course, bigger than 0, meaning I do have to split my contribution and give part of the contribution to steel. All right. Now, at this step, I know I need steel, but I have to do 2 checks before I proceed. All right. What are the 2 checks? First, I need to check the section size. Okay. So what I mean by that is I want to compare, which is VS required, VS required. Okay, that is required steel equal to a 39.3 kips. And I want to ensure this is smaller than 8 times of square root F prime C BWD, okay, which is 130.6 kips. Okay, so why do you call it, or why do we call it section size? Because this is a section related properties. I want to make sure that I don't rely on the web reinforcement too much. If this exceeds the 8 times, if else, right, if it's not satisfied, I need to change the section to be bigger. Okay, but now I'm okay. Okay, now I'm okay. All right, so this is the first check after you know you're going to need a shear for web reinforcement. A second thing is that, do I need to have the spacing? Do I need to have the spacing requirement? Okay, so how do we know that? VS required has to equal to 39.3, calculate already, and has to be smaller than 4 times of square root F prime CBWD. Okay, in this case, I compute this one to be 65.3 kips. Okay, and I'm okay. But if not, or if else, if not, reduce S max to halved. Okay, if not, reduce the spacing for halved. Okay, so for these two cases now, I'm okay. So the check is completed. I can then go to my maximum spacing. So S max directly would equal to least of, don't forget, smallest number, least of the following equations, right? So first of all, has to be D over 2. And that gives me a 10.75 inch, we know it. Okay, and then 24 inches, and then AVFYT divided by 0.75 square root F prime C B W, okay, which is 23.2 inches, okay, and then AVFYT divided by 0.50 BW, and that is 22 inches. So Bob, what are the calculation process? Because these 4 are inherited from here. I got them 4 already here, isn't it? I still use these 4, okay? Still use these 4. And I just have to mark here, this is assuming number 3 stirrups. Okay, so why recompute? I have done this before, and these are the spacing requirements, so I'm going to keep using it. But on top of these 4, I have to add 1. I have to add 1, okay? So what do I need to add? This is AVFYT multiplied by depth D, okay, and divided by VS required. And that is additional computation, okay? Additional computation. So this, let's bring the number in here. Assuming number 3, so 0.22 inch squared, and FYT 60,000 PSI, and D 21.5 inch, and divided by here, and VS required equal to 39.3 kips, and multiply by 1,000 pound per kip. Just convert everything to PSI and pounds, okay, and inches. And now I got this number to be 7.26 inch. And of course, right, observing all these 5 numbers, right, 5 numbers, it's not 4 anymore, and this one governs. 7.26 governs. Okay, so what does it say, right? What does it mean? It means that the spacing provided has to be smaller than S max, which equal to 7.26 inches. All right, so I'm going to say for the safety measures, I want to use a denser stirrups, right? Shorter spacing, smaller spacing. So I'm going to use number 3 stirrups at spacing of 6 inches. Okay, that satisfies the requirement. Satisfy the requirement. Okay.
Professor?
Yep.
How do we know when we have to do the additional check there?
Yeah. So additional calculation come from actually here. Okay. When I know that my concrete section is no longer sufficient, I immediately know that I need to compute VS required. Like I said, A and B cases where concrete is sufficient, I don't have to compute the web reinforcement. Okay. All right, so that's where I already know I'm gonna go in and calculate this. And when I see this, that is not 0 or smaller than, that is not negative, so it means I need shear reinforcement. So before I go in and check the section sizes and half spacing requirement and find out that I'm okay, then I'm going to go in here, and that is the extra calculation gives me 7.26. I'm going to use that. All right. Okay.
Okay, thank you.
Yeah, no problem. Okay. So now that is a first case that we realize we have to use web reinforcement, have to make calculations for it. Okay. All right. So next case, I'm just going to keep increasing my shear. So I had fun with my 54. I said, let's jump up to 77 kips. Why? Because I like it, right? Because I know this is going to be bigger. And so I look at this number. I say, look, obviously, VU equal to 77 kips. And that is bigger than VBC, which is 24.5 kips. Oh, sorry about this. Messed up. 24.5 kips. So I know I definitely need to compute VS required. The steel has to play. The steel has to play. So again, let's just follow it. So VS required from the previous calculation, that is VU divided by phi minus VC. So the number is 77 kips divided by 0.75 minus a 32.6 kips. And this gives me a 70 kips on the money. 70 kips. Okay, 70 kips. And my 7 has a dash in it just to differentiate from 2 or 1. Okay, so 70 kips. So now I know not only I need to compute VS required, but also this number is quite substantial, right? So I'm going to go back to my 2 checks. Okay, one is section size. Remember from previous problem C, section size, and that is VS required. Oops, that VS required equal to a 70 kips, which is definitely smaller than 8 times of square root f prime c BWD, and that is 130.6 kips. All right, and for now, if I say, how about half the spacing? Half the spacing. Okay, so this is okay, by the way. So for half spacing, I have VS required equal to 70 kips, but this number is bigger, okay, bigger than 4 square root f prime c BWD, which is 65.3 kips. So no good. Okay, and what happens? No good. If it's no good in second, we have to reduce spacing by 50%. Wow, that's a big reduction, isn't it? That's a big reduction. Okay, so when we say the 50% reduction, does that mean, Bob, you just take this S here and divide it by 50%? No, no. The 50% reduction only applies here. Okay, only apply here. So halved spacing applies here only. Okay, only applies to these 2 terms in the spacing requirement. Okay, so I'm going to show you, right? So with that, that is the requirement. So S max should equal to a least of. All right, so I know it's going to be 50% off. So D instead of divided by 2 is now divided by 4. So that is 5.3 inches. All right, now next one, it was 24 inch and now divided by 2, which is 12 inch. Okay, and now AVFYT divided by a 0.75 square root f prime c and BW, and this value stays. All right, this value stays, and which is 23.2 inch we calculated before, and then AVFYT divided by a 50 BW, and that equal to 22 inch also stays. Also stays. And the last one is the computed one. Don't forget AVFYT and multiplied by D divided by VS required. Okay, and that is crucial, right? So this bring the number in 0.22 inch squared multiplied by 60,000 psi and multiplied by 21.5 inch and divided by required shear, which is 70,000 pounds, 70 kips. And I got this number to be 4.1 inch. Okay, and this is actually the smallest, right? This is actually the smallest. So this number governs the spacing. Okay, now to ensure I have enough, right, stirrups, so I'm just gonna say I'm gonna use number 3 stirrups. And don't forget, right? Don't forget, this is all under assumption of assuming number 3 stirrups. You say, Bob, do I have to use number 3? No. If you want to use number 4, only thing changes is the cross-section area of the reinforcement AV here. All right, AV here. Okay, so which means this number here. If anything changes, that is the only thing need to be changed. But anyway, so I'm going to use number 3 stirrups at a S equal to 4 inches. And mind you, that is smaller than the maximum spacing governing value, which is 4.1 inch. So I'm okay. All right, so I'm okay. All right, so that is how we're going to handle half the spacing requirement. Okay, but the game is not over yet. I'm going to push my shear up to the limit. I say VU, let's even make it more. So 128 kips. Substantial, right? So I saw this number, I would say, you know, this is too much. This is too much. I know this is bigger than VBC, so web reinforcement definitely needed. Okay, and also I can tell you I just need to compute VS required automatically, right? So that is VU divided by phi minus VC, so 128 kips divided by 0.75 and minus VC, which is 32.6 kips. So I got this number to be a 138 kips. Okay, needless to say, this is very big. This is very big. But, right, I'm gonna go ahead and say 2 checks, right? I still need to check. And I kind of have a prediction that I will fail my section size check first, right? How do I, so see, this is required, and that is 138 kips. Okay, 138 kips, and this is indeed greater than 8 times square root of prime C BWD previously calculated to be 130.6 kips. That means I rely too much on the reinforcement. Okay, so in this case, I say no good. Okay, I need to do what? I need to increase section size. All right, so how do I increase section size? All right, now you have to keep in your head that for flexure, and this is reminiscence of what we have talked about before, just want to box it up here, okay? So I would just put a mark here, says this is digress, right? This is away from what we're talking about. So for flexure, when section is inadequate, oops, section, okay? When I talk about section, I mean the concrete section size dimension, all right? So when the section is inadequate, okay, we increase D. Okay, we increase D for flexure. But for shear, okay, when section is under condition of Vs required is bigger than A times square root F prime CVWD. In this case, okay, we increase width first. Now, what is that? All right, this is a little bit more advanced topic, but just want to quickly explain a little bit on this. Is that when you have a deeper beam, the shear mechanism is a little bit different. It can be more brittle. All right. So second of all, usually when you check the shear capacity, your flexure is already adequate. By changing the height, it's going to critically change your moment of inertia I, and also change your lever arm JD, hence impede the strain that you can exert it to the steel. That means you might have previously a yielding section, which is under reinforced, to transist to a transition zone or over reinforced case, and that is bad. So in essence is that when you try to adjust the section for shear, you're trying to preserve whatever you have calculated for flexure. Okay, all right. So that's just for additional tips, very practical for your design. But anyway, so this is the tips. I know now it's better to change the width rather than the height. So now I'm going to take a look at the section, and the section was 12-inch in width, and of course 24 in height. Say, you know what, let's just bump up, right? And I'm gonna make it a little bit wider. And again, this drawing might be a little bit disproportional, and this is 16 inches. Change it to 16 inches. And the height stay the same. Okay, height stay the same. And to make it a little bit more beefed up, right? To make it a little bit more beefed up, I can do what? I can also consider increasing F prime C. Okay, F prime C. All right. But you may also wonder, say, hey, Bob, you just said when you're trying to change the section to accommodate for shear design, you don't want it to interfere with the flexure as much as possible. But now if you change F prime C, it's going to change your shear design, isn't it? Yes, it does. But you got to figure, right? It is easier to change the compressive strength than change the height of the section in some cases where the height has limitations, right? Especially in a parking garage and high-rise buildings where you have a very strong limitation on the floor height. All right. So the last measure is to change the concrete strength, and the last measure is change the height. Okay. But normally in our practice, at this point, we're just going to increase the section and go back to drawing board to look at A, B, C, D, E, these 5 approaches, and see which one applies under the increased section. Okay. So this one is over for E. All right, we'll stop at E. And in exam, we will most likely not have E, but A, B, C, D. Okay. All right. So I'm going to pause for a second. Any questions on this, folks? Anything, guys? Anything? All right. So I hope this is clear. And this is very, very important. Okay. Design for shear. All right. I have like a few minutes. So let me just start a little bit on the critical section. Okay. All right. So now, okay. Now I want to open up a small side topic, which is actually important, but is critical section for shear. Oh, sorry, for shear design. For shear design. Okay. Now, this is a long example. You might need to read it several times to digest, which is understandable, and ask me questions whenever you have them. But I just want to go back to see this small details here. Okay. And I draw you the section, I draw you the diagram, shear diagram, and labeled where exactly the critical section is at, which is spacing ds away from the edge of the support. from edge to support. You may have a question, say, Bob, so every time when we see a support, we do like that. We pick this critical section to find out the shear force, because you see the maximum shear force is actually here, right? It's at the end. It's not exactly the critical section. So why you do that? Why you do that? Because that's in the code. Because that's in the code. All right. And you normally would not develop that shear of VU max in reality. The maximum shear you're going to develop is on the critical section where the first diagonal crack occurs. First diagonal crack occurs. Okay. Then this begs the question, right? What are these critical sections? How we define them, right? And how we label them in the real structure. So this is what this objective is going to talk about, right? So this talk about. Okay, so first of all, let's show, right? So sorry about that, let me just change it. So list of critical sections in the code. Okay, and this is in ACI 4.4.3.2. Okay, and this is same for 318.14 and 318.19. This hasn't changed. This hasn't changed. It's very important. Okay, this is very important. If you cannot find it, let me know. Okay, if I mislabel it, let me know. But this will be in exam number 2 for sure. Okay, will be in exam number 2 for sure. All right. So what does it list, right? So let me draw it up. Okay, let me draw it up. So in case A, and don't forget, this is under distributed loading, okay? Distributed loading. Just put it right in front. So in case A, I have a very typical simply supported condition, okay? SS, simply supported, okay? Make sure you know that. And then for simply supported case, let me draw the drawings. I have a side view of beam resting on the column, right? Resting on the column. So you see that, right? Let's just assume it's a steel beam and I have some, ribbed support. Okay, this is the rib support. All right, I want to draw it as clear as possible. Okay, as clear as possible. And this usually is a rocker, so it will create a simply supported case. And if I can draw it more clearly, if you see this, this is more like a hinged steel plate, and then hinged. Okay, pinned it somewhere, and this is on the base. Okay, so it can rotate, free to rotate, right? To simulate the simply supported case. Okay, simply supported case. Anyway, so at the end of the bottom here, right, will be the junction where you see this whole thing, rocker is sitting on the neoprene pads, which is a little bit wider than the rocker. Okay, and now after that, you see the column underneath it. Usually it's a flushed to leave space for the adjacent span. Usually it's a flush. And the columns here is way wider than the neoprene pads. Way wider than neoprene pads. Okay. Now assume this is distributed load, right? Distributed load. So, of course, I have my distributed loading sitting on top of the beam, just like so. All right. So I'm going to tell or decide where I'm going to pick the critical section. Okay. So red line, and this is the center of the support. Center line here. All right. And this is the edge of the support. You see that I'm putting it right on the edge of the neoprene pad. This is edge, and that is the starting line. And you go horizontally a distance of D away from it, and that is, ladies and gentlemen, is my critical section. Okay, so this is my critical section. Okay, and why is that? Because, and you need to draw this in your exam as well, okay? Because I will have a diagonal crack 45 degrees, like that. Like that. All right. So it is correspondingly in the shear diagram, right? In the shear diagram, remember? So this will be the rocker. Maximum shears should be here, V max. VU max actually, right? And then if I do a drawing, right? Remember, I do a drawing. Oops, this is not realistic. So I do a drawing, and excuse me, it cuts right here. Of course, extended somewhere. It should be crossing the 0, but that's fine. And the distance right here is D. And then this value here, folks, is the VU for design. All right. So that is very important. You need to know where is that locations at when we design for. Okay. Okay. All right. I'm just going to stop here. This is only one part of the list. I'll finish the list next lecture on Wednesday. But with example, you're ready to do homeworks. Okay. The last problem of homework, I might have to explain on Wednesday, but we're in good shape roughly. All right. So I'm going to stop here and welcome any questions, folks. Any questions for me, guys? Are we all good? Anything? No?
Yeah. Well, it is about me, so I'll wait for the
Yeah. Okay. That's fine. Yeah. If there's no personal questions, I'm just gonna stop recording